Hello, in this video I want to talk about optimization, what it means and how we can use calculus to find it. Optimization means effectively finding either the highest or the lowest value of a particular quantity. And with a graph, I think I can show you how calculus might help us to do that. Let's say that we have a graph of some function of x that maybe looks something like this. Alright, so that's some function of x. We see that this graph has a local maximum or high point about there. I'm going to say that that's at about here. I'll call that x equals a. And a low point or local minimum there, which I'll say is x equals b. Now you may recall that from a graphing standpoint, the derivative tells us the slope of a graph at a point. At the point at x equals a and the point at x equals b, the slope of the graph would be 0 there, which means that the first derivative f prime of a is 0, and the first derivative here, f prime of b, is also 0. So what this graph might suggest is that if we're interested in finding a high value or a low value of a particular quantity, and if we can model that quantity as some sort of a function, then it would make sense to look for that high value or that low value at places where the first derivative is equal to 0. There's only one slight hitch to that. As this graph suggests, that first derivative is 0 regardless of whether you have a local maximum or a local minimum. So the problem is basically if you found some value c where the first derivative equals 0, did you find a local maximum or a local minimum? Yeah, so if f prime of c is 0, did you find a local maximum or a local minimum? And what's worse is you may have found none of the above. It's possible for the first derivative to be equal to 0, and it's neither a local maximum or a local minimum. So we have to try to answer that question. And unfortunately, just taking the first derivative at the local extremum doesn't really help. We need some more information. Fortunately, there are two tests that help us out in this. One of them is the first derivative test. If you look up the first derivative test in any calculus textbook, you'll find a lot of words. So I'm going to try to explain it somewhat more simply by way of a graph. So let's say for this graph I'm about to draw, we'll see a local maximum, which looks to occur at about there. I'll call that x equals c. And then I'll pick a value slightly less than c, or to the left of it, x equals a, and a value that's slightly to the right of c, making it greater than c. I'll call that x equals b. So we know that the first derivative is 0 because we have a local maximum there. So let's say we have the first derivative at c equals 0. What the first derivative test says in this situation is that if the first derivative at a is positive for some value a nearby c but less than it, and if the first derivative at b is negative for some value b greater than c but nearby, then we can say without a doubt that f of c is a local maximum. There's no longer a toss-up. It's definitely a maximum. There's no question maximum, minimum. It's definitely a maximum. Now the other situation that the first derivative talks about, I'll show you that in a moment. So let's draw another graph, this time one that will have a local minimum, like that one. Alright, so it looks like that local minimum is about there. I'm going to call that c. And then again, I'll pick a value slightly less than c. I'll call that a. and a value slightly greater than C. I'll call that B. So we see in the graph that since there is a minimum at C, the first derivative there would be 0. So we'll say that. We'll let the first derivative at C be equal to 0. What we see in this graph is that the first derivative at A this time is negative, right? So if the first derivative at A is negative, for some value A that's less than C but nearby, and if the first derivative at B is positive for some value of B greater than C but nearby, then we know without a doubt that f of C this time is a local minimum. There's no question. So the first derivative test then is one test that helps us to determine if we found a case where the first derivative is 0, whether that tells us we found a maximum or a minimum. Another test that we could use is known as the second derivative test. Now, just to give you some background on the second derivative, we know that numerically the first derivative of a function tells us the rate of change of that function. The second derivative, being the first derivative of the first derivative, if you will, tells us about the rate of change of the first derivative. Now, from a graphing standpoint, as we said, the first derivative gives us the slope of a graph at a point. So what the second derivative tells us from a graphing standpoint is the rate of change of that slope. So let's say that we have this time a graph of a function where it looks like there's a local maximum right at that point at C. Looking at the slope and sort of riding along on the graph, letting x increase, the slope is positive, 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 but it's decreasing. It's going down until it gets to 0 at C. And then it continues to go down, so it becomes negative and more and more and more negative. So what's happening throughout this interval is that the slope is decreasing, which means that the first derivative is decreasing, and therefore the second derivative is negative throughout this interval. And that's key. It's negative throughout this interval as well as at the point where x equals C. So what the second derivative test says is this. Let's say we have a value C at which the first derivative is 0. If the second derivative turns out to be negative, then without a doubt f of C is a local maximum. Okay. Now let's draw the other scenario to see what the second derivative test will say when we have a local minimum. You might be able to guess, but we'll have that up in a moment here. So here we go. So this time we'll have a graph where we have a local minimum. And again, we'll say that that's about there. So I'll call that point C. Now, if we look at the slope of this graph and kind of ride the curve and let x increase, we see that the slope is extremely negative here. It becomes somewhat less negative, which means that that slope is increasing. It's increasing into 0, and then it gets positive, which means that it continues to increase. The first derivative is increasing, which means that the second derivative is positive. So we know that there's a local minimum in this graph at x equals C. So we'll say that. We'll start that off. Let f prime of C be equal to 0, as it would be in this situation. If the second derivative at C is this time positive, then f of C is a local minimum. So that's what the second derivative test tells us. So we have not one, but two different ways to sort of answer that question, which is the question being, if we find the first derivative equal to 0 someplace, have we definitely found a local maximum or a local minimum? And as it turns out, there are advantages and disadvantages that might compel you to favor one test over the other. If you have a particularly complicated function and it's bad enough to take the first derivative, you might not want to take the second derivative, so you might go with the first derivative test. On the other hand, one thing that's nice about the second derivative test is that you only have to look at that critical point itself. You only have to look at the place where the first derivative is equal to 0. You don't have to look on either side as you would in the first derivative test. So there's some advantages and disadvantages either way. I'm going to do a part 2 video on optimization where we will use these concepts to actually solve problems and try to find either the maximum or the minimum value of a certain quantity. But in the meantime, thanks for watching.